Hi there, so in this video I'm going to provide you with a preview of polynomial functions and their graphs. So just below that here you see that I've defined a polynomial function, what the graph of it should look like. It should be a smooth, continuous curve, meaning that but it should not have any sharp corners, it shouldn't have any breaks, it shouldn't have any holes or asymptotes in the graph of a polynomial function. In other words, you should be able to smoothly trace it without any sharp corners. Okay, you would never have to pick up your pencil and not have any sharp corners, and then for certain then you are a polynomial function. So if I scoot on down here to example 1, I've given you 4 examples here of graphs, and I ask, well, which of these are examples of polynomial functions? So we'll just say yes or no here, whether they're polynomial or not. So if I look here in letter A, you think about, okay, well, if I were to trace over this graph, I never have to pick up my pencil, and I don't have any sharp corners, not any holes or anything like that. So letter choice, or graph A here definitely is a polynomial function. If we move over to letter B, though, and look at this graph, I can draw one portion of the graph without picking up my pencil, but I can't get the other portion of the graph, so this is not a polynomial function. And then if we look down at letter C, hopefully you recognize, well, hey, there's a problem with this graph. What does it have? It's got a sharp corner down here. This is actually the absolute value function, so it is not a polynomial function. And then lastly, if you move over to letter D, is that a polynomial function? Yes, it is. There are not any breaks or any holes or asymptotes in that graph. We can completely trace over this graph without picking up our pencil, and there aren't any sharp corners. So yes, that is a polynomial function. All right, we'll move on and start getting a little deeper here into our polynomial functions and their graphs. The next piece I have down for you is a fact, basically a couple of definitions. It says the degree of a polynomial is the degree of the term with the highest degree. So whenever we want to determine what the degree of a polynomial is, we need to find out what the degree of each term is, and then whichever is the highest, that is the degree of the polynomial. I'll demonstrate that for you here down below in example 2. The leading coefficient is the numerical value in front of that leading term. So you'll notice here, if we move on down here to example 2, all of these are examples of polynomials. They want us to state the degree of the polynomial and then tell if the leading coefficient is positive or negative. One thing that I'll go ahead and point out to you, in letters A through D here, if you notice, these polynomials are in what we refer to as descending order according to the variable. And so your degree is always associated with the exponents. So you'll notice here in letter A, this is x to the first power, and then the second term doesn't have any x's. If I move down to letter B, this is also in descending order. You have x squared, x, then number. Look at letter C. You have x to the fourth, x cubed, x squared, then number. So it's going down in descending order. I'll always encourage you when you're working with polynomial functions that if you have a polynomial that is not given to you in descending order, to put it in descending order, because when you do that, the degree is going to be the first term, and your leading coefficient will be right there. You'll just be able to pluck everything off that you need. But nevertheless, if we look here, so we know that these are in order. But in terms of finding the degree of a polynomial, you look at it term by term. So the degree of the first term, exponent there is a 1. The degree of any number is always 0. So the highest degree here is 1. 3x would be referred to as your leading term. So I'll write that for us, that our leading term here would be 3x. We want this, and then the leading coefficient is just the 3. It's just the numerical value. And so all that I'm asking you here to identify for me is the sign on that leading coefficient. Well, it's a positive 3, so we're just going to put a positive. All right, and then we notice, we'll do one more of these all the way. So looking at our degree. So here, the first degree of the first term is 2. I'm looking at my exponent. Degree of 3x is 1. It's imaginary 1 there. Degree of any number is always 0. We pick the highest, so we know our degree here is 2. Again, my leading term, so my leading term this time is just that first piece there, negative 4x squared. And then the coefficient in front there would be negative 4, so the coefficient sign would be negative. All right, I'm going to scoot on down and do letter E with you. Because letter E, you'll notice, is a little different. The only thing that's different here is you recognize that it's not foiled out for us. So we can just quickly foil this. We know x times x squared, outside minus 2x, inside minus 1x, and then last will give me a positive 2. So then I have, clean it up, minus 3x plus 2. Now I can say, okay, here's my leading term here, right up front, so we can say that this polynomial is degree 2, and the sign on that, an imaginary positive 1 in front. Okay, so technically, if your polynomial, again, is in descending order, then the degree is just going to be the exponent of that very first term of the full polynomial, and we're going to build upon the signs over here on the next page, because what the signs and these degrees do is they tell us about the end behavior of our graph. Okay, so I encourage you at the moment, pause the video so that you can check yourself and with the solution key, but I'm actually going to go ahead and fill this in here as well, but you might want to pause the video, make sure you can do C and D, and then come back, and then make sure that you agree. Hopefully you agree with these answers for both of those last two. All right, let's flip it on over, and on the next page we're going to be putting a little bit more to, like I said, this degree and the leading coefficient sign, and actually reference back to this example. So at the top of the page, first bullet point says that if a polynomial function has a positive leading coefficient, okay, so I'm just saying that number out in front at the very first term there, if it has a positive leading coefficient, then its end behavior will be up on the right-hand side of the graph. And so what I mean by end behavior on the right-hand side of the graph is that for both of these graphs over here that I've drawn, this is the right-hand side, this is the right-hand side, and you'll notice that it is going up on both of those pieces, okay? So if we go back and look at example 2, we want to figure out then, well, which one of those polynomials, we can just identify it by the letters, they were A through E, will have end behavior on the right-hand side. So we need to go back and focus on which one of those graphs on the previous page had a positive leading coefficient. So if we flip back over, which ones had a positive leading coefficient? Okay, so that was letter A, letter C, and letter E, right? All of those had positive leading coefficients. So if we were to identify this, if we were to start graphing these in our calculator, we would see that all three of those would be ending up on the right-hand side. So A, C, and E. Next bullet point down says, well, if a polynomial function has a negative leading coefficient, then its end behavior will be down on the right-hand side. So I've drawn two graphs over here so you can see what that looks like. Here's your right-hand side, I'm going down. Here's your right-hand side, I'm going down. Remember, read a graph like you read a book from left to right. So now go back and look at your example 2, which ones are going to have end behavior of being down on the right-hand side. And hopefully you agree. Okay, well that would have to be B and E. B and D, excuse me, B and D. B and D. So come back over here, B and D. All right, go a little deeper here. And their next bullet point says that if a polynomial function is an even degree polynomial, then its end behavior is going to be the same on both sides of the graph. And what that means is that the graph will either go up on the left and right or down on the left and right. So that's what we mean by having the same behavior on both sides. Okay, so it's either going to be up, up, or down, down. So we want to go back and look at our even degrees now. Which of our polynomials would have the same end behavior? Okay, so if we go back and look at our even degrees, so my even degrees, let me use a different color so I can keep this just kind of going a little different. Okay, so my even degree was here in letter B, letter C, and letter E. Right, those are the ones that have even degrees. So since they have even degrees, then we can say that they are going to have the same end behavior. So we would say here B, C, and E. And then our last bullet point here says, well, if a polynomial function is odd degree, then its end behavior is going to be different on both sides, meaning it's going to be up, down, or down, up. Okay, so go back and look at, okay, well, which one of our examples over here were odd? Odd degrees would have to be A and D. So we would list here as A and D. So just below here, we will summarize our polynomial functions and their types of end behavior. Basically, there are 4 types. Your end behavior can be up on both sides, down on both sides, up on the right, down on the left, or down on the right, up on the left. So basically like up, down, and down, up. Below that, I look at it even a little differently here. I say, okay, well, if your leading term is positive and it's raised to an even power, then your graph will go up in both directions. And so what that looks like then is that we are up, up. If your leading term is negative and it's an even degree, so a negative raised to an even power, then your end behavior goes down in both directions, so down, down. So basically with your even behavior, you're always going to have the same, you're always going to be going in the same direction, and if it's positive, you go up, if it's negative, you go down. So that's hopefully very intuitive for you. And then we'll look at odd behavior. So if you are positive raised to an odd power, then your graph rises from left to right, so that means you are down and then up. If you are a negative being raised to an odd power, then you are going to fall from left to right, so that means you are up and then end up going down. Okay, so those are your 4 pieces there. So now with that said, I'm going to give you another opportunity down here below in this table to kind of dissect it again. Okay, if you have an even degree polynomial and a positive leading coefficient, then your end behavior is going to be what on both sides? Hopefully you agree that I have a positive even, so that's going to be up on both sides. So we can think of that as up, up. Okay, I'm going to let you finish filling in the table. Everything is there for you on the solution key to check yourself by. Okay, so let's flip it on over to the next page. And here in the next example, I say, well, now let's determine the end behavior of these particular graphs. So if we look at, let's say we do, well, perhaps I'll just go ahead and do them all. If you want to pause the video and try some on your own, by all means do so. Okay, so if you notice here in letter A, we have all of our leading coefficients are right here, these first terms. So I have a positive value, and this is to the first power, so we know 1 is an odd number. So odd behavior is always going in different directions, but since it's positive, that means it's going to end up going, it's going to be rising from left to right, so that means it is down then up. And you can write it, if you prefer to just write down and then up instead of using arrows, by all means do that. Notice the next one, leading coefficient is negative and it's raised to the second power, which is an even number. Remember, evens always go in the same direction. Because it's negative, we are going to be going down, down. Okay, so, or you could write that as both down if you like. Okay, look at your next one. You have a positive raised to an even power. So remember, even always goes in the same direction. Because it's positive, we're going to be going up, up. So we can write both up. The next one, you have a negative being raised to an odd power. Since it's negative, that means it's going to be falling to the right. So that means we start out going up and end up going down. So it is up, down. And then that last one, we really only have to worry about multiplying the first term. So x times x will give us x squared. So here we have a positive raised to an even power. And so sure enough, again, we know even always has the same direction because it's positive. We're going up in both directions, or you can write both up. Okay, think about, a graph over here like letter A that you already know, like y. This is y equals 3x minus 9. You know that that's a linear line. It has a y-intercept down here at -9, and then my slope is up 3 over 1, up 3 over 1. And so sure enough, on the left-hand side of the graph, it's going down, and on the right-hand side of the graph, it's going up. Think about letter B here, and -4x squared. You know that that's a parabola, and because that 4 is negative, that it faces downward, right? So, and sure enough, when we were just identifying our end behavior, we said both down. Okay, so that's the connection there. Okay, all right, a couple of bullet points down here below. The maximum number of x-intercepts a polynomial can have is the same as its degree. Okay, so if you have degree 5, then you can have a maximum of 5 x-intercepts. The maximum number of turning points of a polynomial can have one less than its degree. So if your degree is 5, then it can only have 4 turning points. Remember, turning points from a previous lesson that we talked about are where you change from increasing to decreasing. Okay, so here, like this little graph that I just drew, I have 1, 2, 3 x-intercepts. So this could be a degree 3 polynomial, and then notice how it has 1, 2 turning points. So that's what we say, one less than its degree. So degree 3 has 3 x-intercepts, and then 2 turning points. This is just a maximum, though. This technically could be a degree 5 polynomial, and maybe the other 2 zeros are imaginary, for example. Okay. All right, we'll move on down then to example 3, and I'm just going to do letter A and B here with you. Okay, it wants us to give the maximum number of x-intercepts and the maximum number of turning points of each polynomial based on its degree. So here in letter A, f of x, I'm still using the same example throughout this whole lesson pretty much. We'll notice here in letter A, I've got this polynomial 3x minus 9, so we know the degree on it is just 1, so it's the first degree. It can have up to then 1 x-intercept and up to 0 turning points. Think about, again, we just graphed this. We said this was a linear line. Here's your y-intercept down here at -9, and it's increasing. And sure enough, it's only crossing the x-axis in one spot, and there aren't any turning points on a linear, right? Because you have to change from increasing to decreasing or decreasing to increasing. So look at your next one. This was a polynomial of degree 2, so it has second degree polynomial. It can have up to 2 x-intercepts and up to 2 minus 1, so 1 turning point. And sure enough, that's exactly what we know to be true about this graph, right? Because we know that it's a polynomial facing downward, and it is going to cross the x-axis in 2 spots, and it's going to have 1 turning point there at its maximum. Okay. All right, I encourage you to pause the video and try C, D, and E. Make sure you're tracking with that and check yourself by the solution key. And then we'll move on down here below that. And it says, well, in the example above, all of the functions are presented in expanded form except for one. Which function is not presented in expanded form? And hopefully you would agree that that would have to be letter E down here, where we had f of x equals x minus 1 times x minus 2. It's not in our expanded form, it's in what we referred to as factored form. Okay, and fact down here below, it says if a polynomial function is presented in factored form and you wish to know the degree, then you're going to need to add the multiplicities of all the zeros. So you might be saying, well, what is multiplicity? Flip it on over and I have that definition for you. The multiplicity of a zero is the number of times a factor corresponding to that zero appears in factored form of the polynomial. Or in other words, if you have a factor that has, so like here, if this is we have like this, we have x minus 2 times x minus 3 squared. Then this first factor here has a multiplicity of 1 because it has an exponent of 1. This next factor here is going to have a multiplicity of 2. Now, technically, we don't think of them as the factors having multiplicity. We think of the zeros having multiplicity. And we know how to find zeros. Zeros are where we set our factors equal to 0. So that's what we'll be doing here in example 4. Example 4 wants us to state the multiplicity of each zero and then find the degree of your polynomial. So in letter A here, we're using that same polynomial that we've been using. I need to find the zeros, so we find it's already in factored form, so we take our factors here and set them both equal to 0 and solve for x. So it's just a one-stepper here, so x equals 1, and over here add 2 to both sides, so x equals 2. So we have zeros at 1 and at 2. The multiplicity, or the exponents on those factors, and the exponents on both of those factors are 1. Okay, you can then add the multiplicity down. 1 plus 1 is 2. That tells us that we are degree 2. We had previously found out that we were degree 2 by foiling. Okay, so I just want you to just kind of see that correlation there. Okay, now if I'm going to let you let's do letter B here together since it's a little different. So here in letter B, you'll notice that this is in factor form. You have x. We would set x equal to 0. We would set x minus 2 equal to 0. X plus 5 equal to 0. X minus 4 equal to 0. And x plus 6 equal to 0. We would set all of those terms equal to 0 and solve for x. So we know with that first one, we set it equal to 0, it's already solved, so you have a 0 at 0. The next one, if we set this equal to 0, solve, we're going to have a 0 at 2, negative 5, positive 4, negative 6, right? Because I'm just going through and I'm taking all of these equations and I'm just doing that quick solve there. Okay, so that's all I was doing for each of those. And I'll let you continue that if you need to. Hopefully you're getting to a point where you can kind of eyeball it. Now your multiplicity goes through and looks at the exponent. So the exponent on that first x is just 1. Exponent on the factor x minus 2, also a 1. The next exponent, so that negative 5 would have a multiplicity of 2. We're going to expand on multiplicity here in just a moment. 4 has a multiplicity of 3. And negative 6 would have a multiplicity of 2. And then if you go through and add down now, this whole column here, I'm going to start here from the bottom. 2 plus 3 is 5, 6, 7, 8, 9. So this would be a polynomial of degree 9. Okay. Alternatively, if you want to think about, how we can do this, and I think I have actually that's coming here in the notes, so I won't jump ahead of myself. All right. I have you recall down here a fact that we've already talked about. Remember that your zeros of a function correspond to the x-intercepts on your graph. Okay, so if we have zeros, this is where we're going to be crossing or bouncing off of the x-axis, and that's what multiplicity tells us. Fact just below here, it says that the multiplicity, and I want to highlight this because this is important, the multiplicity of a real zero tells you if your graph will cross through the x-axis or if it will bounce off of the x-axis. When you have an even multiplicity, then your graph is going to bounce off of the x-axis. When your multiplicity is odd, then the graph will cross through the x-axis at that particular zero. All right, so if we move on down here to example 5, then we already know what the zeros are of this function. We found it just above here, so we can tell, okay, well, this has a 0 at, remember we found our zeros. We would just set x minus 1 equal to 0 and x minus 2 equal to 0, so our zeros are at 1 and 2. The multiplicities were our exponents up here, so 1 on both of those. Since both of these multiplicities are odd, then that means we are going to be crossing the x-axis on both of those. Okay. And so essentially what that's going to allow us to do is that, okay, well, we know that we have zeros at positive 1 and positive 2. And we can think about in behavior, right? X times x, our leading term here would be x squared. So this is a positive raised to an even power. So my in behavior here is going to be the same direction, so it's going to be up, up. And so this would be a rough sketch of this graph here. We foiled this out a few minutes ago and we said it was x squared, minus 3x plus 2. we should expect that it to be a parabola facing upward, right? And so that's where we're headed, okay, is that, okay, well, this multiplicity here tells me that I get to cross through both of these zeros here. When your multiplicity is even, what we mean by bouncing is that maybe you get to cross through one of your zeros and then bounce off, like, so we'll say here's a 0 and here's a 0. This is an example of crossing the x-axis. This is an example of bouncing off of the x-axis right there, okay? So that's what our multiplicity is telling us, whether we cross or bounce off of the x-axis. All right, let's flip it on over then to the last page. I'm going to let you try that next one. I'm not asking you to graph it or anything, but just to, you already know what the zeros are and you already know what the multiplicities are. Tell me now if it's going to bounce or cross, because we've already filled in this column. So if you remember, if you're even, you're going to bounce. If you're odd, you're going to cross. All right, and then we'll do one more here together. I say, okay, well, let's basically put it all together, and that's actually what I actually just did in that last problem. I really did get ahead of myself, unfortunately. That if we take our leading term here, x times x, we have x squared, and I'll go ahead and full it out for us. And then we had plus 2 when we fulled it out earlier. So we can say, okay, well, this polynomial is degree 2. The leading coefficient is a positive 1. In behavior then, because I have a positive, I'll write it like here, positive raised to an even power is going to be up, up, or you can write it as both up. Okay, and then I will let you try letter B there. Okay, all right, let me know if you need anything. Thanks a lot. Bye.